well, same as the week before, will be kicked out in about half an hour, and then we'll use the same dress and so on. Today we continue to prove regularity properties for elliptic operators. And well, the general name for those properties is elliptic regularity, which is something that that is specific to the elliptic case, and which is not at all true for general differential operators. Let's recall what we sorry about that. Let's recall what we did last week. Suppose we have two vector bundles. It's working. Let me change the size of the board. Let's suppose we have two vector bundles. On a smooth compact manifold without boundary, we normally assume that the manifold is. I don't think. Well, for elliptic regularity, we don't actually need to assume that the manifold is orientable, but we did use a volume form to construct various scalar products. So let's not assume that the manifold is orientable, and at some point, if we need orientability, let's just ask ourselves whether or not we really need it, what we can do with that. And I think the answer will be we can do with that. Okay. Now T. From smooth sections to smooth sections is an elliptic operator. Okay, now we proved last week that the kernel and the co-kernel are finite dimensional, which is already something. But apart from these properties, we also need to know that the image is closed and complementable. And let's prove this. This was one of the properties which I stated a while ago, and we use this property to prove a few things about elliptic complexes. So it's something that we already used, and let's prove it. And this would follow if we managed to prove that the kernel, sorry, that the image is the orthogonal complement of the kernel. The orthogonal complement in the L2 metric, which we defined on the sections using well, as I just said, using a volume form, but there is a way to do it, and having a volume form is equivalent to the manifold being orientable. But there is a way there's a workaround which also works for non-orientable manifolds. Anyway, so we we would prove what we're after if we're able to prove this. But let's also note that there is a similar formula which is completely for free, namely the orthogonal complement of the orthogonal complement of the image is the kernel. Now, but the formula we want to prove is not for free. Sorry. Maybe this formula isn't for free. Let's also recall that D star is the joint differential operator, which is also elliptic. Does everyone remember what the joint operator is? It's a joint with respect to the L2 metric, which we introduce on sections without taking any derivatives into account. In other words, it's the W naught metric. Are there any questions? Okay. Well, let's prove a proposition. Well, suppose I have suppose I have a psi a smooth section of f such that psi is orthogonal to the kernel of D star. And then there is a smooth of E. There is a smooth section eta of E such that psi is d of eta. Again, orthogonal means orthogonal with respect to the L2 metric. And well, if we're able to prove this, then as a consequence, we will get this this equality. Well, the equality basically one inclusion. The orthogonal complement of the kernel is inside the image. This is the proposition. And what about the other equality? The image is inside the orthogonal complement of the kernel. Well, this other inclusion follows from the free formula, which says that the orthogonal complement of the image is the kernel of the joint operator. So in particular, every element of the image is orthogonal to the kernel. Is this part clear to everyone? And by the way, does everyone understand why the equality in D equals kernel D star orthogonal implies what we're after? Namely, why this equality implies that the image is closed and complementable. Yegor, do you understand this?
Можете, пожалуйста, повторить?
Ну вот, значит, мы хотим доказать, что образ замкнут и дополняем. Даже не обязательно орто дополняем, просто дополняем. Вот. Мы говорим, что это следует из того, что значит, образ это дополнение к чему-то. Значит, вот как из второго следует первое.
Взять дополнение еще раз.
Ну, пригодно. Ну, в общем, в бесконечной мере это, кстати, нужно осторожно.
Да, есть такое дело.
Значит, well, let's go through this again. So the well, first of all, the orthogonal complement of every subspace in a Frey-Hilbert space is closed. So there are no surprises there, which is basically straightforward from the definition. But the kernel the kernel of D star is finite dimensional, and this is crucial. Every subspace, every finite dimensional subspace of a Frey-Hilbert space is the orthogonal complement of every finite dimensional space is complementable, and the complement is okay. I'll write it down. So suppose we have a Frey-Hilbert space, subspace. Then the orthogonal complement is of a subspace is always closed. Moreover, the subspace does not intersect its orthogonal complement. But it is not always true that let me write it. Let me write this this way. W plus W orthogonal is not in general equal B. But it is if V is finite dimensional. Sorry, if W is finite dimensional. If W is finite dimensional, both W and W orthogonal are complementable. Okay, now well, let's prove the proposition. And the proposition, recall, was this one. Suppose I have a smooth section of F, which is orthogonal to the kernel of the adjoint operator, which we know exists, and we prove this quite early in September or October. Then this section is T of eta, where eta is a smooth section of E. Okay. We'll be kicked out. We'll be kicked out in 10 minutes. Well, let's see if we manage to prove the proposition before that. Anyway, so what do we have? We have well, we have D. No, sorry. Okay, well, D, which goes from C to C infinity of F. and well, let's remember that we have several extensions. The WM V to WM. Sorry. We'll only need one sublet extension, so I'll write this. I'll write this this one. What is M? Well, sublet extensions in particular. In particular, the one that ends up in W dot. Where which one is it? Well, it's dm, where m is the order. The order of D. Okay. Now, well, once we have a map of vector spaces, we have the dual map, and the definition is well, the definition is straightforward. And well, basically, it's basically linear algebra. Now, the only difference is we consider the continuous dual, meaning the space of continuous continuous linear maps on the respective Hilbert spaces. Okay, now let's use the following trick. let's identify the spaces with the dual spaces with the complex complex conjugate of the sublet spaces with minus the index. How do we do that? Well, let's do this in the second case. In the first case, the strategy, the formula will be exactly the same. So suppose we have a section y inside W minus M of E, and X is inside W M of E. I define the action of y on x as the L node, sorry, the W node scalar product of x and y. And in other words, again, I'm using the volume form, but this is not really necessary. I integrate x times y bar against the volume form. Now, this integral is in general not well defined, but it is well defined if x is inside W minus M and y is inside WM. Okay, sorry, less than 1 minute. Okay, I save the notes. Let's just use the same link once the time runs out. Now, the next